Welcome. On an abstract outset, we have seen what a vector space is and an example of a vector space in the previous lecture. Now, continuation to the previous lecture, we will see few more examples of a vector space. Here, we will start with some well-known fields, that is the set of all rational numbers, set of all real numbers and set of all complex numbers. Here, we know that set of all real numbers is a subset of set of all rational numbers is a subset of set of all real numbers, which is a subset of set of all complex numbers. In the previous lecture, what we have said is that if we have a field and a subfield, that field is a vector space over the subfield. Using that idea, we can say that the C is a vector space over R. Similarly, C is a vector space over Q, as well as C is a vector space over C, because C is also a subset of itself. This is going to happen. Now, let me check R. Using that idea, we can say R is a vector space over Q and R is a vector space over R. Now, let us prove R is not a vector space over C, because let me take any real value. Okay, let me take some value from this. Here, that is, I am taking something like this. Okay. Now, when you make a scalar multiplication, the result must be in R. Alpha plus IB times of AX. I do not have a guarantee that this is a member of R. If it has to be a member of R, then I must have that beta part is 0. But that is not true always. Therefore, we can see this is not a vector space. Similarly, Q is a vector space over Q. But Q is not a vector space over R, as well as Q is not a vector space over C. These two are not vector spaces. Right? Next, we are going to consider the set of all m cross n matrices whose elements are taken from the field F. So, here V is the matrices of order m cross n, where each entry is taken from F. We have to prove this is a metric space over this is a vector space over the field F. For which, what is the vector addition defined here? The vector addition here is the usual matrix addition, that is, term-wise addition is going to be the vector addition in this case, and usual scalar multiplication of matrices is going to be the scalar multiplication in this case. Right? If we have to prove this is a vector space, what are the things we have to check? We have to check this V with respect to the matrix addition is an abelian group. Okay. Now, let me have Aij is to be added with Bij. This is an element taken from B. This is also an element taken from B. Therefore, the addition of these two matrices is well defined, and that is going to be something Cij. It is also of the order m cross n, where each element Cij is Aij plus Bij. This Aij and Bij are the entries taken from F, and F is a field. The addition is true and the result is also in F. This proves the closure. Right? And matrix addition is always associative, and the zero matrix of order m cross n is going to serve as a zero element in this set. And for uh, for Aij, the inverse is going to be minus Aij. And this is associative, and this proves the first condition to be a vector space. Next, what should we do? We have to prove some scalar into the matrix is a member of V. We need to prove this. Okay. What is it? When you consider this, it is going to be alpha times of Aij for all Ij. Since this entry as well as this entry are taken from F and closure is true under multiplication in F, we have this to be a member of V. Next, when you have this can be written as alpha plus beta times of Aij, and you multiply and you can segregate this. And this happens to be alpha times of Aij plus beta times of Aij. Okay, and when you multiply a scalar to the addition of two matrices, this also happen to be this in the trivial sense. First you will have to add these two matrices, then multiply the scalar, and now separate those two terms. Okay, you are going to get this. And when you multiply one with all the entries of the matrix remains unchanged. Having satisfied all those conditions, you can promote the set of all M cross N matrices where the elements are taken from any field F is a vector space over the same field F. We have come to the end of this lecture, and we will see few more examples in the upcoming lectures. If you have any queries, you can post it in the comment box. Thank you.